In the very beginning, there was only an endless vacuum in space and a singularity. The singularity was composed of all the matter and energy we see in the universe today, all held together by an unimaginable amount of gravity that squashed it down to the size of a football. Held together by gravity for a length of time that we simply cannot comprehend. Eventually, the singularity became unstable and exploded. Eventually, the plasma in the universe cooled, and therefore single electrons and protons were able to stick together to create the first very basic atoms. Because the sticking together of the protons and electrons was an exothermic reaction, a reaction that gives out energy rather than absorbing it. A particle of energy was released that flew off in a straight line incredibly fast. In fact, at the speed of light, because it was, in fact, light. The particle is called a photon. And in fact, photons are what light actually is. Photons had existed before this, but now, because of the change in the universe, from being composed of essentially plasma to now being made up of gas, as mainly hydrogen built up in the universe, the photons were now able to freely fly through space. These photons flew throughout the universe, which was dark because there were no stars at all. These photons, created out of the formation of the first atoms, were the only light in the galaxy. Eventually, gravity, which is referred to as the weak force in physics, began to pull the atoms of the universe together to form clouds of hydrogen, which eventually became so dense that the heat and friction between the hydrogen atoms got so high that they ignited into stars. Stars fuse two hydrogen atoms into helium in a process called nuclear fusion. It is nuclear fusion that is used in modern nuclear weapons. The first nuclear weapons were nuclear fission bombs. They released huge amounts of energy by splitting the atom. However, nuclear fusion releases a far greater amount of energy, and that is why nuclear bombs of today use the fusion method. Just like a nuclear bomb, stars emit huge amounts of energy and light, except that they do it on a larger scale and also continuously until their death. Without stars, the universe would be a very dark place. And without our star, the sun, the Earth would be incredibly dark. Dark enough, in fact, that no plant life would grow, and therefore no other life could exist, including us humans. Our sun gives us life, because it gives us warmth and light. Without it, Earth would be just a dark and frozen planet. So, we now know what light is, but that was not always the case. The ancient Greeks believed that light came from our eyes. But this theory was eventually given up, as people wondered, how then is it possible that one can sit in a dark room? If light came from our eyes, then the fact that you are in that dark room with your eyes open should result in that room being illuminated as the light is emitted from your eyes. Muslim scientists began to examine the characteristics of light as they discovered the rules of reflection and the magnification properties of glass lenses. It was obvious to humans at this point that light was all around us and was a force of nature within the universe. At this point in human development, science was very sparse. So, for that reason, it was not until the scientific revolution, which began in 1643, that we really started to understand light and all of its characteristics. A few years later, in 1652, a Dutch scientist called Christian Huygens was exploring optical phenomena. He studied how light bounced off surfaces and how it traveled through glass. He had noticed that light would change direction when it went through glass, and so was the first person to identify refraction. Reflection is the process by which light bounces off something, like a mirror, whereas refraction is the process in which light changes direction as it travels through a medium like water or glass. What was particularly interesting was that refraction did not just alter the course of the beam of light, but it also could split that beam into many colors and produce patches of light and dark. Due to this, it became obvious to Huygens that light was some kind of wave that oscillated. Oscillation is a perpetual rhythmic change that is seen throughout nature and the entire universe, in planetary orbits and in vibrating electrons. We see and feel waves all around us as we go about our lives. When we listen to music, we are interpreting sound waves. When we drop a stone in a pond and watch the ever-expanding ripples, we are watching a wave. Another scientist named Robert Hooke also came to the conclusion that light was a wave. This, however, was not agreed upon by Sir Isaac Newton, who insisted that light was instead made up of tiny particles. He came to this conclusion because with sound, you can still hear the sound, even if there is a physical object blocking the sound from you. Because as a wave, it would spread and bounce around. Whereas with light, if a physical object was between you and the light, you will not be able to see it. You cannot see an object if another physical object is placed between you and the object. Unless that is, if the object that is between you and the other object is in fact transparent, like glass. Going back to the splitting of light into various colors, it is interesting that we humans think of light as being white or transparent, but that in fact there are so many colors of light, and some at an energy scale that we cannot even see. Until the 19th century, we did not know of the existence of infrared light. The reason that infrared light cannot be seen by the human eye different colors. In fact, there is no such thing as colors. Colors are just an image that is placed inside your brain by your neurons as they interpret a particular wavelength of light as being present. When you see blue light, it is because light ranging from 380 nanometers to 500 nanometers has gone through your eye, hit your retina, and your brain, having received the signal from this, interprets it as blue. As the light changes from 380 nanometers to 500 nanometers, we see varying types of blue. And it is for this reason that there are so many shades and tones of all the colors that we see. Without the information that is caused by light, our brains have nothing to interpret. So our brains interpret that lack of information as black. So, out of this, the question must arise as to how we see black during broad daylight. How can it be that in broad daylight, when light is bouncing off everything, we see black? The answer to this lies in the reflective nature of an object. Different objects reflect different wavelengths of light. If an object takes all of the wavelengths of light and absorbs it all, except those between 380 nanometers and 500 nanometers, then what we see is blue. If an object absorbs all visible light, so that none of it goes into our eyes and hits our retinas, then the brain is receiving no light or color information. In that situation, the object appears black because our brain interprets that lack of information as being dark. So, what about the opposite of black? White. How do some objects appear to be white? In the opposite way to black, objects that appear white do so because they literally reflect all of the wavelengths of light, and therefore no wavelength is predominant, and as a result, your brain interprets it as white. So, if an object that reflects all visible light appears to be white, then how do mirrors work? Should they not appear to the human brain as being white? The difference between a mirror and an object that appears to be solid white is that of scatterization. An object that appears to be white to the human brain reflects all of the light that hits it. But because very few surfaces are actually smooth at the microscopic level, at the nanometer level, the individual light photons that hit the irregular surface of the object scatter around, and therefore what you get with the crossing of all these reflective beams of light is essentially a featureless block of white, as it is interpreted by your brain. A mirror, on the other hand, has a completely smooth surface. So when light hits it, it reflects it at exactly the same angle that the light hit it in the first place, and therefore it does not disrupt the image and creates a perfect specular reflection. But why do some things appear to be transparent or see-through? Transparency is caused by the transmission of light waves. If the vibrational energy of a light wave is passed through the object, then the object appears to be clear or transparent. If the energy only causes vibrations in the surface before reflecting off the object, then the object appears to be opaque. So the reason glass is transparent is simple. Visible light can pass straight through it. on the subject of light passing straight through objects. There is a light that can pass through many more objects than visible light can. This light is called X-ray. In 1901, the Nobel Peace Prize in Physics was awarded to a German scientist called Wilhelm Röntgen for what he published about the nature of light as he discovered the X-ray. Wilhelm Röntgen discovered that not only the most dense materials could stop X-rays flying right through them, he noticed that if you hit the human body with X-rays, that the X-rays would go straight through skin, but would struggle to get through bone. And so, because of this, he was able to take a photograph of a person's bone structure. This was obviously a massive development in the medical world, as for the first time, doctors could see what was going on inside of the body. This was particularly useful in order to detect broken bones. However, as X-ray technology developed and was fine-tuned, it was able to be used to detect more subtle changes in density. This increase in the sensitivity of detection led to X-rays being able to detect and observe the differences in density of soft tissue, so that tumors could be identified. But what is an X-ray? An X-ray is a type of light very similar to ultraviolet light, in that it has a shorter wavelength than visible light. The only difference between ultraviolet light and X-ray light is that the X-ray has an even shorter wavelength than the ultraviolet ray. One thing that all light has in common, no matter what its wavelength and energy is that it always travels in a straight line. However, this is not always the case, because light can be affected by gravity. Gravity is described as the attraction of one thing with mass to another thing with mass. So how then can light be affected by gravity when light has no mass at all? If light were to obey Newton's law of gravity, then gravity would have no effect on light. However, a more modern take on gravity is that of Einstein's general theory of relativity. Einstein's theory of relativity suggests that gravity arises from the curvature of space and time. It suggests that large objects alter the geometry of space and time to create a gravity well. So even if light has no mass, it can still get caught in an object's gravity well, and therefore have its trajectory and direction altered by the much larger object. In fact, light can even be trapped by large objects, like a black hole. The reason a black hole is called a black hole is because it looks black. The reason it looks black is because, unlike our planet Earth, which looks blue and green because blue and green light is reflected from it, a black hole reflects and emits no light whatsoever. This sounds similar to what we discussed earlier with objects that look black because they absorb all of the colors of visible light. But in fact, it is very different. The black hole is not absorbing all the light that falls into it. It is, in fact, holding the light so close to it with such a strong force that the light cannot escape, and therefore all you see is darkness when you look at a black hole. Inside of a black hole, there is an insane amount of mass, all being crushed together at immense pressure. If there were to be an explosion inside of a black hole, you would not see it. However, if the same explosion happened on Earth, you would see it. You would see the explosion on Earth, because the explosion, like all explosions, creates energy and light that flies off into space to be seen by the eye or by a telescope. If an explosion happened inside of a black hole, then this explosion would also emit light. But as soon as the explosion happens, the light would be pulled back down towards the black hole. So although the light had been emitted from the explosion, you simply would not see it if you were observing from space, because in order for the eye or the photoreceptive chip of a telescope to see it, the photons from the explosion would have to reach them, which they would not. It is interesting to think that you could actually be right next to the explosion that took place inside of the black hole, and yet you would not see it. Because before the photons from the explosion get to your eye, they would be sucked back down into the black hole, so all you would see is darkness. But light is not just affected by gravity. It is also affected by magnetic fields. The northern lights, or the aurora borealis, are beautiful dancing waves of light that have captivated people for millennia. But for all of its beauty, this spectacular light show is a rather violent event. Energized particles from the sun slam into Earth's upper atmosphere at speeds of up to 45 million miles per hour. But our planet's magnetic field protects us from the onslaught. As Earth's magnetic field redirects the particles towards the poles, this dramatic process transforms into a cinematic atmospheric phenomenon that dazzles and fascinates scientists and sky watchers alike. As we know, our planet gets dark at night. Nightfall is caused by the fact that we are on the other side of the planet to the sun. Our planet is essentially blocking the light from the sun from reaching us. Even X-rays that can travel through a lot of substances cannot travel through the entire body of Earth. However, our sun is not the only star in the galaxy. And our sun is not as large as most. So why do the stars not keep the night side of the planet light? After all, there are at least 100 billion stars in our Milky Way galaxy. Not to mention the infinite number of stars out there in the universe. The reason that the stars of our galaxy do not light up the Earth at night is because they are so far away, and because the light spreads out with distance. It results in only a tiny fraction of it reaching Earth. It is also worth noting that many or most of the stars in the universe could not light Earth because they are so far away that the light from them has not had enough time to reach us. The universe is approximately 13.7 billion years old. But some stars are so far away that the light from them, even though traveling at the speed of light, has not had time to reach us. This limit on being able to see things in the far reaches of space is referred to as the observable universe. You can only see something in the distance if the light from it has had time to reach you. If there is no light, then there is no sight. It is also worth noting that scientists believe our universe is still expanding. So as some light travels towards us, the distance that it has to overcome in order to reach us is constantly getting bigger. It is also worth noting that there are objects between us and the stars. Some as small as lone atoms that float around in space. Many refer to space as a vacuum, but in fact, there are many objects in space, from planets to lone atoms to free protons and electrons. These objects also block light from reaching Earth, and so also reduce the illumination of Earth from the stars. One of the biggest questions in physics, which raged on for hundreds of years, was the question as to whether or not light was a wave or a particle. The scientific community switched between concluding that light was a wave or light was a particle many times as various experiments by various scientists appeared to prove one way or the other. Now it is presumed that light simply has both wave and particle properties. One of the reasons that light is thought to be a particle is because light can have an impact on other substances, whereas a wave cannot. When light shines on a metal, electrons can be ejected from the surface of the metal in a phenomenon known as the photoelectric effect. This process is often referred to as photoemission. and the electrons that are ejected from the metal are called photoelectrons. It seems from this that light can create a pushing effect, even though light itself has no mass. It is for this reason that it is thought that light could one day be used to propel a spaceship or even push an asteroid away from Earth. The idea would be to constantly reflect the sun's rays onto the asteroid to very slowly change its direction. The push from the photons is very small, but over a large span of time, it could just be enough to push an asteroid off target. On the subject of using light to power a spaceship, the spaceship would end up looking very much like a sail ship, as it would be a ship with a massive sail. It is strange to think that a spaceship could end up looking much like the original ships that crossed our oceans, especially when you consider that there is no wind in space. A sail ship works because air molecules have mass, though there is very little mass in each one. But because so many of them are bashing into the sail, together they create a good push. The use of light on a spaceship works essentially the same way. Every time a photon hits and reflects off the spaceship's sail, it gives a little push, as there is a transfer of momentum. It is important to note that I use the word reflects, because in order to get maximum push from the protons that hit the sail, it is important that they reflect rather than just absorb, so that the maximum amount of push is given to the sail and therefore the ship. This push, along with the fact that there is no friction in space, can create enough of a push over time to accelerate the ship to incredibly fast speeds. This may seem like the stuff of science fiction, but the Japanese have a light sail called Icarus, which has already been proven to be effective. So this sounds identical to how a traditional sailing ship is pushed by the mass of each air molecule hitting it. However, there is a difference in that photons do not have mass. In physics, we learn that momentum equals mass times velocity. So therefore, no mass means no velocity. However, in quantum mechanics, velocity can be caused by energy. And of course, photons do have energy, so they therefore can create velocity. So, why use light to power spaceships and satellites? The big advantage of using light to power things is that it is free energy and therefore makes space travel much cheaper. You would be able to travel anywhere in the galaxy with no fuel costs. However, it is worth noting that if you were to land on a planet, then this would take up fuel, as you would need energy to come in and land in the appropriate spot. And you would need even more energy to leave the planet, as you would be fighting against the planet's gravity. However, once in space, you would be free to roam the stars with no energy cost at all. Some may ask, why not use light to escape the planet? Well, the reason for this is that you need light to hit from behind the sail, which is impossible when you are actually on a planet. And because the power from the light is small, it is not enough to explosively overcome the gravity of a planet. However, light is used on Earth in industry. As we know, much of the power that we use is created by solar panels. This, however, is very different to how a solar sail works. As discussed earlier, with a solar sail, the ideal situation is for the photons of light to reflect off the sail in order to create the largest push. With solar panels, the opposite is the case. A solar panel works by absorbing energy from the protons, which creates an electrical charge that moves in response to an internal electrical signal field in the cell, causing electricity to flow. We as humans have so many uses for light, whether that be industrial, to sterilize surfaces, or for social and entertainment reasons like discotheques, fireworks, and watching TV. However, most scientists would agree that we have only just begun to understand the possibilities that light could give us one day. There are over 100 billion stars in our galaxy, constantly emitting light throughout space. It is a constant free energy source that we have only just begun to tap into. Without light, there would be no life, as nature has become so embroiled with it that it simply could not survive without it. In the future, when humans have managed to spread themselves to the stars, we will need to find a way to harness this free energy that surrounds us in all we do. But for now, we live in a world of light, just waiting for the technology that will one day set us free from our planet and thrust us into open space.